Hello, everyone. The title of the talk today is about how we are leveraging Walmart Retail Graph to power seller similarity. Before we go further into the presentation, a quick context setting about the presenters. My name is Arun Menon. My fellow presenter is Prashant Rao. We both belong to the US Omnitech org within Walmart Global Tech. I'm a distinguished ML engineer, and Prashant is a staff engineer. We both belong to the Retail Graph Initiative. As a precursor, wanted to touch upon our vision statement for marketplace. A lot of what we are talking about today stems from this vision statement. We want to become the most trusted and preferred global marketplace. We need to do this by building a platform rooted in trust, transparency, and fairness that exceeds customers' expectations and grows seller business. Why do we need to scale our marketplace? We'll look at it from Walmart and seller lens. Growth potential. Global marketplace revenues have shown explosive growth in the last few years. It's only natural for us to carve out our share from this pie. Assortment. This helps assortment breadth while reducing inventory risk. Builds customer risk and loyalty by capturing long tail demand. Pricing. Offer density promotes competitive pricing. Profitability. uh, Commission has direct correlation with profits. Sellers. Traffic. Sellers can use the Walmart traffic to increase sales. Speed. Ability to onboard items much more faster. Payment cadence is also much more faster. Control ownership of content, pricing, inventory, fulfillment, and customer service returns. Marketplace seller footprint has been growing exponentially year on year. WFS, which is Walmart Fulfillment Services, has been the chief catalyst for this growth within the seller ecosystem. We are keen to increase our seller growth rate in the coming years. I want to talk a bit about seller grouping. Challenges as we scale our marketplace. How do we find seller neighbors? The definition of similarity is dynamic and ever changing. We need to look at various features and traits of a seller in a much more holistic way to make that determination. How to generate seller clusters holistically in an unsupervised manner. Are these factors important? This is a critical step as we personalize seller recommendations. This is going to be very vital for seller analytics as we increase the seller footprint. This makes sense. This makes the seller vetting process more streamlined, robust, and automated. This is absolutely critical for us as we enter the hypergrowth phase within the marketplace. Some of the challenges with the existing solution that is currently that is what we are currently using for seller grouping. Rigid. We only leverage item inventory overlap score as a feature for computing distance metric. Adding more features to compute similarity is not straightforward in our existing pipeline. Time. Doing pairwise similarity calculation at scale is proving to be prohibitively expensive. What are the implications of that? We currently restrict pairwise calculation against terminated sellers only. That is a very small subset Um, we want to ideally include live sellers when we do our scans. Similarity scores that are provided currently give a very partial view since we don't include live sellers. To offshoot our cloud costs, we run similarity calculations once in 2 weeks. Uh, Seller similarity scores are therefore not real time. The need of the hour is a platform which can give a holistic view of a seller. This will greatly aid in seller similarity analysis. We also need a compute platform that can speed up the feature generation task without being prohibitively expensive. Enter retail graph. What is a retail graph? It started out as an item centric knowledge graph. It has now evolved into a data fabric layer, which gives a connected view of the various retail data domains that you see here. The domains we manage in our data fabric layer are items, seller, taxonomy, pricing, rest of market, search engagement, and entities. True to the philosophy of data fabric, we keep synthesizing new knowledge from our connected model continuously. This knowledge, which is fed back into the data fabric layer, will enrich it further. This will set off a flywheel in motion where knowledge synthesis will be self-sustaining. Seller similarity is a classic case in point. I want to talk about the retail graph value proposition in context of seller similarity. Uh, Retail graph is able to provide us graph features for sellers at scale quickly. What do we mean by graph features? A characteristic which is based on the pattern of connections within the seller group graph. This is a new and powerful capability. This approach is much more flexible compared to the earlier approach, which was only tied to a specific feature. As a result, the graph features become more richer as more and more data domains are added into our graph/data fabric layer. Want to talk about how the want to talk about the approach we use to generate this graph feature. We want to talk about the seller embedding generation approach. But before I talk about that, I wanted to give some context setting on what a graph embedding is. Is it a technique for feature extraction? Is it a technique for dimensionality reduction? Is it a technique for representation learning? I would argue that it's all of the above. As you can see in the diagram, we have a seller graph and we have this encode seller step, which is what I was referring to as the seller embedding generation step. The encode seller looks at the seller attributes and seller neighborhood patterns to generate the seller embedding. This is where this technique is more holistic compared to the other techniques which are non-graph based. Uh, Once we have the seller embedding generated, the decode seller neighborhood step that you can see can help us find seller neighbors. And this is what we are trying to do in a nutshell. We have the encode seller step and we have the decode seller step. And the embedding that you see is basically the graph feature that we were talking about. We looked at the following techniques for generating graph-based seller embeddings. We looked at node to vec, which is based on random walk. We looked at FastRP, which is a form of matrix factorization. The tabular representation that you see are the algo runs we did on our seller graph sandbox. Our seller graph has 50,000 vertices and close to 8 billion edges. FastRP has a lower time space complexity vis-a-vis node-to-vec. In our runs, node-to-vec could never finish completely on our sandbox and would blow up with out-of-memory errors. I'd like to switch over to a 30,000 view of our architecture. On the right, we have our data lake. This is the repository for all the data domains that you saw previously in our data fabric slide. We have a hybrid ingestion pipeline for all these data domains. We have a batch and a near real-time pipeline, which transform these various data domain elements into a canonical vertex edge message for ingestion. We have an entity extraction pipeline also, which is currently leveraging our common large language model based inferencing layer. All these data domain elements flow into our graph data fabric layer, which is powered by Tiger Graph. At this point, I would like to switch focus to seller similarity. The seller similarity calculation is split into two stages. One is the seller embedding export stage, and the second stage is find seller neighbors. Both these steps are running on a daily cadence. Under the seller embedding export step, we leverage FastRP to generate seller embeddings. These embeddings are then exported to Vamos. What is Vamos? Vamos is our internal vector similarity search offering. Once the seller embedding step is done, we run the seller neighbor step, and it recomputes a neighborhood for all the sellers. The first step is where for a given seller, it finds the top K nearest neighbors. This seller neighborhood information is then fed back into the RG data fabric layer. This is the step that I was talking about, where we continuously feed back any new knowledge back into our fabric. This seller neighborhood information is also dumped into our pick query tables, where it is picked up by Seller Analytics platform. So this was a brief overview of our architecture. With this, I will pass on the baton to Prashant, who will drive the rest of the talk.
Hey Arun, thanks for setting up the seller similarity context. Now I will be walking through the implementation details of the seller similarity. Firstly, how do we go about generating the seller embeddings using retail graph? And secondly, how do we leverage these embeddings and find the neighborhood sellers? Before going there, I would explain a bit about the FastRP algorithm, which is basically used to generate the seller embeddings. FastRP is a node embedding algorithm in the family of random projection algorithms. This is a scalable and performant algorithm for learning distributed node representations in a graph. The basic premise of this is, one can project n vectors of arbitrary dimensions into log n dimensions and still approximately preserve pairwise distances amongst the points. Now, to translate this in a graph world, what this means is, two nodes with similar neighborhood should be assigned similar embedding vectors. Right. So the key success of the FastRP algorithm lies in the fact that how the node similarity matrix is constructed. Here basically what happens is all the transitive relationships in a graph is considered, and also the matrix is normalized based on the node degrees. And once we have this, the dimensionality reduction is applied by using the sparse random projection. So now that we have a fair idea of FastRP, let me just explain some of the learnings we have had using the FastRP algorithm. So firstly, we have started to leverage node attributes in the FastRP embeddings calculation. So there could be different node types having different attributes, wherein the attributes themselves could be vectors. So what we are currently doing now is use those vectors as a part of the eventual embedding. So as you can see in the example, the way it was initial versus the way it is once those vector embeddings have been added as part of the final seller embedding. So the eventual dimension will still remain the same, which is 384, but the overall quality of the embedding would have greatly increased after this. And secondly, the ability to create different flavors of embedding. So there are easy configurable ways to add or delete node types, or even the edge types while we are running the FastRP algorithm. So by doing that, we can generate different kinds of embeddings, which can be again used for different purposes. And also it is an easy way to find out the embeddings quality during the benchmarking. And the last one point is on the batch versus the non-batch mode flow, right? So initially, when we were running the FastRP algorithm, it was run on the non-batch mode, where the target vertices were around 100K, and with edges being around 1 billion, and the total size of the graph was having approximately 2 billion vertices and around 8 billion edges. We had observed a big spike in both CPU and memory during the run. So then we had to collaborate with the Tiger Graph team, and then we came up with a strategy to have this run in the batch mode, where the first step is again to run a connected components algorithm and identify different components in a seller graph, and then use those subcomponents to basically trigger the different batch flows and run FastRP in multiple iterations. So that way, we have been able to complete the FastRP runs within our stipulated time, and also without too much pressure on both CPU and memory. So now I'll be explaining the two steps that we have for the seller similarity pipeline, wherein the first step is the seller embedding generation phase. So as I already talked about, again, pre-processing is something that we do to identify all the seller connected components, and then generate the seller embeddings by running the FastRP algorithm. Now, once these embeddings are created, we are exporting these embeddings to a platform called VAMOS, which is a vector similarity search platform that supports multiple index types and has support for different distance metrics. So this also gives end-to-end lifecycle management for vector embedding. So there's an internal platform that we have developed, and again, APIs are exposed to find approximate nearest neighbors. The APIs are fast and scalable, which caters well to finding similar sellers in near real time. So once once we have these embeddings, we then push it to VAMOS via the APIs. The seller collection is basically stored in graph-based HNSW index type with 384 dimensions. So this HNSW algorithm is actually pretty fast and accurate, and it also suits pretty well to the scale of the seller embeddings, which is around 100K. However, when we benchmark this against the collection size close to 500 million vectors for some of the other use cases, results were not that much optimal. Yeah, and the next step, once we have these embeddings pushed to VAMOS, is to find the seller neighborhood. This is done by using ANN techniques for finding all the nearest sellers for a specific seller, and then publish the key nearest neighbors to RG and also to the BigQuery table. So how we publish it to RG is there will be a seller to seller edge that we'll be creating for all the nearest sellers. And then the edge weight would basically be the similarity score that we'll be getting out of the in inserts. So this is on the publishing part. So this is just to give an illustration of how exactly we find the nearest sellers for a given seller. So first thing is to get the seller embedding, which is obtained by hitting in year cache, wherein we have stored all the seller embeddings. And once we have these seller embeddings, we'll be pushing it to Vamos, where we'll do an ANN and get the top key nearest sellers and push it to the downstream. Now, what exactly is the impact of seller neighborhood pipeline that we have created using retail graph? So the cadence has definitely increased. Initially, it used to be 2 weeks without this graph approach. Now it's almost done on a daily basis. And we definitely want to increase this cadence even further. And also, provision for seller similarity in near real time. So that is something that was not available earlier, wherein we have the APIs now, the seller match APIs, basically to get us the similar sellers. So lastly, I'll be talking about our next steps. One of the major asks for us, is to ensure a near real-time seller similarity, which means having a cadence in few minutes to an hour. To make that possible, right now we are looking at different algorithms, and Notebase is something which is high on our priority list, mainly because it's a compositional and parameter efficient representation of a large knowledge graph. It ensures a drastic reduction in the memory footprint, as it does not need to store embeddings on all the nodes, rather only on a subset of nodes called anchor nodes using the encoder functions. Now, if there is a new seller for which we need to generate an embedding which is attached to the seller graph, the embedding can be generated on the fly by using the same encoding function, thus making this algorithm extremely efficient to operate. Also, we are always on the lookout for improving the seller embeddings quality. One way to definitely do that is by adding more meaningful signals into our graph. So this is possible because both the seller graph and the algorithms that we have been using are easily extensible. And lastly, we would want to also explore more on the hyperparameters. Some of them, like the number of hops and their corresponding weight. We have done multiple iterations and we have generated different kinds of embeddings. Yeah, we would definitely need to optimize it further, and we are working progress towards that. Well, I think that is all we had to say for this talk. It has been a great pleasure for us to be part of this conference. Thank you everyone who attended this talk. Enjoy the rest of the conference. Thank you.